Salamanders. Okay, thank you, I guess, for that introduction. So I'm going to talk about our work on understanding this thing called message franking that was relatively recently deployed by Facebook. And this is joint work with some other fine people, Evgeny Dotis, Paul Grubbs, Jiawei Liu, and Joanne Woodage. So we are in this setting of end-to-end encrypted messaging. So there's this idea that you can get on your chat client on one end, send a message through some service provider, for example, Facebook, and have it received and read by someone on the other end with an end-to-end security guarantee that the service provider, despite helping you with this service, can't read or modify any of these messages. Metadata type things we heard about earlier revealed like who you're talking to, but at least the contents of messages are protected. And this has been like one of these amazing success stories in the last like several years, right? I mean, TLS took decades to kind of get deployed widely on the internet, but we've seen just this huge surge of end-to-end messaging encryption mechanisms that are now being used like by literally billions of people every day. And that's because of major providers like WhatsApp and Facebook and Signal that have become very popular very quickly and have supported this kind of new confidentiality guarantee. So the cryptography underlying these end-to-end encrypted messaging systems is non-trivial. So there's a lot of new ideas that have built off various things in the research literature, like Diffie-Hellman ratcheting, and how to position keys to make sure key exchange works very well. For the purposes of this talk, we're not going to focus on any of those details, and I'll just refer you to this kind of nice set of work that's emerging to formally analyze and understand some of these other cryptographic portions of end-to-end encrypted messaging. Instead, we're just going to think about encrypted messaging as already having a shared secret key. In fact, this secret key is only used for one message, and it's used to do authenticate encryption with that message before sending it. Authentic encryption just meaning it's not only providing confidentiality, but also authenticity. No one can modify the message that's sent. You can't even generate a new ciphertext. Okay, so having this great end-to-end security guarantee is fantastic, but it comes at seeming odds with various other features that service providers want to provide. So one thing that Facebook particularly wants to do is help users with abuse. So if instead of sending some nice message, someone sends an abusive message, they want the recipient to have the ability to report to the service provider that this mean person said something harassing, maybe made fun of your Twitter feed or lack thereof. So this is great, and in a plain text messaging service, this would be trivial or not trivial, but this would be straightforward to implement because they have visibility into the messages sent. But again, here we're using cryptography, and the end-to-end security guarantee means that the service provider has no way to know a priori that this was in fact the message sent. And so this opens up to avenues of abuse in turn that like someone could frame someone as having said something if you kind of implemented this in a naive way. So Facebook was savvy to this tension, and it seems like something that's kind of at odds, right? But they came up with this clever idea of having the recipient, or when the message is sent, having the ability to basically generate a cryptographic proof of the message contents when reporting abuse that's like verifiable. So this idea of verifiable abuse reporting. And they call this idea message franking. I guess the idea is this is like to be frank about your message franking. It's a cute name. Okay, so this is in 2016. They talked about this at Real World Crypto, and we saw it, and it looked pretty interesting. But that said, they wrote a white paper. I think they talked to some cryptographers to consult on it, and they kind of rolled this new cryptographic system, and that left a lot of questions open and things that we wanted to address. So our contributions is that we basically did the first kind of formal and in-depth analysis of message franking. One of the main results I'll talk about is finding a vulnerability in Facebook's scheme. So for example, you can send this picture as an email or as an image attachment in Facebook secret messages. This is an axolotl, which is this endangered type of salamander, which I find very creepy. So this will be my stand-in for an abuse image. So you can send that in a way that's not reportable by the recipient as abuse. It basically you can arrange as a clever adversarial client sender to ensure this kind of disappears, is invisible from the abuse reporting mechanisms. And then we'll take a step back and try to reconceptualize what's going on here. One of the problems is that they kind of assumed implicitly security properties of cryptography that did not hold. And so we're going to formalize a new cryptographic primitive that we call compactly committing authenticated encryption, which we believe is the right, captures the right security properties that you really want in this message franking setting, at least from the low level symmetric encryption primitive. And then we'll provide some of the fastest new schemes that we're now working on, like implementing and hopefully having reference implementations for people to deploy later. There's a pair of papers on this topic, one last year at Crypto, and then the one that'll come up in the forthcoming Crypto. The full version of the old one is available already. The new one should be hopefully up in a few weeks. Or you can email me if you're very curious. So please definitely interrupt and ask questions at any time if you have any. So let's see how Facebook's message franking protocol works. And obviously, I'm going to be skipping over a lot of the details, but I'll give you basically the high-level, most important bits that'll be important for the purpose of the talk. So they don't just send an authenticated encryption of the message, but they add a bunch of other stuff. In particular, what they do is choose what we'll call an opening, this value k sub b. You just think about this as a secret key, essentially, that they choose fresh every time they send a message. And they generate a keyed hash now, an HMAC, of the message M, which in this case is this abuse message. This serves as a cryptographic commitment to the message, and this commitment value C sub b is just appended to the authenticated encryption when it's sent. The now combination of this opening value, this k sub b value, and the message is encrypted using authenticated encryption. In the case of Facebook, which uses Signal, this is an encrypt then HMAC authenticated encryption mode. Then they send this pair, this ciphertext plus this C sub b value. The service provider gets this. Facebook will then actually sign this C sub b as a way to remember that it saw this value when it was sent over the wire and generate this short, again, signature like HMAC in this case, that we'll call T sub FB, and sends that along to the recipient. The recipient decrypts, gets back this k sub b value, checks the commitment is correct, and if all that's good, then shows the message to the client. To do an abuse report now, instead of just sending the message, the recipient can send this k sub b value, the opening. They can open the commitment, again with the cryptographic jargon, send the commitment value and this T sub FB value, and now the provider can verify that HMAC of this message and under the key k sub b is equal to C sub b, and then in turn that T sub FB is a valid signature. So they saw this thing before, and now this basically verifies for them this is the message that they saw earlier. Okay, and there's a lot of other stuff like timestamps and many other things that I'm glossing over here, of course. Now importantly, and this will be relevant to the attack, the way they do attachments and videos is different than this slightly, and I'll show that in a moment. Okay, so this is cute and looks kind of reasonable, but it left us with lots of open questions. Obviously, the most important is whether this is kind of secure. To me, as a cryptographer, I looked at this and said, there actually seem to be rolling a new primitive here, something that kind of combines in some way a cryptographic commitment plus authenticated encryption. So maybe there's really a new abstraction that would be useful in helping kind of reason about the security of these systems. And then, of course, are there faster, better approaches than what they had come up with? So it should be clear, obviously, from what I said before, that the answers to these questions are like, yes, but not for attachments in terms of security. Yes, there is a better formal approach, and yes, there's better approaches. So let me focus, to begin with, on this attack that works against their attachments. Any questions so far before I move on? Okay, good. So to do that, I need to at least kind of informally specify what types of security goals we want for message franking. The first thing that seems relevant to what I said earlier about framing someone as having sent something that they didn't intend, that they did not in fact send, is this notion that we call receiver binding. So the recipient shouldn't be able to open a message that wasn't sent by the actual sender, okay? Can't open a message not sent. There's actually another security property, which we actually kind of realized late in the game, but it's very important, and will be very, very important to the security attack that we showed, which is the idea of sender binding, that I shouldn't be able to send to a recipient a message that decrypts properly, so it gets shown to the recipient, but for which, if the recipient tries to report that thing to Facebook, the verification procedure fails. right? If I can do that, then I can send abusive messages in a way that you can't report them. And that is problematic as well. In addition, we want to maintain our existing end-to-end authenticity and confidentiality guarantees for messages that aren't opened, right? If I don't open a message, Facebook should not have any insight into that message. Okay, so for our analysis, this basic scheme actually does achieve these informally stated here goals for messages, but what they did with attachments doesn't quite work. And in particular, we can show an attack on sender binding. So again, I can send a attachment such that you receive it, but it isn't reportable to Facebook. So let me go over this. So how do they do attachments? So what they do is this kind of key encapsulation type of approach. So instead of sending, just like encrypting the file context directly with this approach that I outlined before, they choose a key for that I called kfile here. That's in turn used to encrypt the contents of the file. And then they use the prior scheme I described to encrypt and commit to this k-subfile. Okay. The reason they do this is because the approach of committing and then doing encrypting that's shown on the top line is kind of slow. It requires 3 cryptographic passes over it because you have to do an HMAC, and then you have to do an encryption, and then another HMAC if you look underneath the hood of what's going on with the authenticated encryption. And they deem this too slow for larger things like images and videos. Whereas instead, by doing this approach, they're able to use a different scheme, AES-GCM, which is one of the most widely used authenticated encryption schemes out there now, and is like really fast. Okay, so that's good. So, and of course, the recipient has all the information they need to recover the file because they can decrypt the first thing with their shared key, get kfile, and then decrypt the attachment. Okay, then to do abuse reporting, what happens is they send the opening for kfile, okay, and the Facebook then checks this opening, and then goes on and decrypts all unique AES-GCM ciphertexts that have recently been sent, and then adds them to the abuse report. So it's a little bit weird because here they're committing to this key, k-subfile. But then that's being used to try to really commit to the contents of the encryption under k-subfile. And there's this gap here that we're going to be able to exploit. The other thing that you might notice is that I put plurals in here, which is a little bit different than what's actually shown on the slide. In fact, when you click abuse report, they don't just send the most recent message, they send the last several messages. And so for example, you can send say 2 files in a row. This is just kind of replicating the same process, but with the number 2 involved in these variables. And when you do the opening, you're going to open both of the openings for kfile1 and for kfile2, and then they're going to go look for these associated ciphertexts and show them. And the second thing that I need to emphasize here is that they only add unique AES-GCM ciphertexts to the decryption of unique AES-GCM ciphertexts to the abuse report. So when they get back this sequence of opening values, they kind of go look up in a database, basically, ciphertext. And if they have already seen one of the ciphertexts, then they don't add the resulting decryption again, and just kind of skip over it. So there's this very interesting gap that we noticed, which is that if these 2 ciphertexts essentially are the same, the AES-GCM ciphertext are the same, but the keys are different, keyfile and keyfile2, they may be able to decrypt to different legitimate plain texts, but only one of them will get inserted into the abuse report. So in particular, if we're able to generate an AES-GCM ciphertext such that it decrypts under 2 different keys to 2 different messages, then we can basically arrange for one of those messages to be like an abuse image and one of them to be an innocuous image. We can send all of that stuff, and because it's the same ciphertext, the abuse reporting logic on Facebook servers will only add the innocuous image to the abuse report, and the other one will effectively disappear from the system. Yes?
Could you elaborate why would they only do this for unique ciphertext, not for all ciphertext? The decrypt correctly.
It's a deduplication mechanism. So they basically take a hash of the ASGCM ciphertext and they use that to identify ciphertext. And for whatever reason, I guess efficiency or something, they decided to, not do these other things. We don't have 100% visibility, obviously, into Facebook's proprietary code that implemented this. Like Signal's open source, but what Facebook's message franking stuff is all proprietary. We were working with one of the engineers to understand it, so I don't have a 100% precise answer for you, but that was our understanding from talking to them. So it's basically a logic bug, but I think informally, actually, you would expect a priori that ASGCM, it should be hard actually to do this, generate a ciphertext that decrypts to two different messages correctly under the same key, unless maybe you've thought about these properties before and realized it's not true. So some intuition here that actually the ciphertext should uniquely identify the plain text, despite the fact whatever key is being used. A little bit of a word salad there, but hopefully you get the point. Okay, so we have this task of showing that we can do this, right? To generate a single ciphertext that decrypts correctly under two different keys.
So why is it that it shows only the innocuous image and not the only one? So is it not the other one? So is it a matter of order? Or what?
Yeah, there's an ordering issue that I forget actually which order you send it in. I think you send the abuse one second and the innocuous one first, and whatever their loop is that's going over things, like just ignores the second one. Yeah. Mm-hmm.
For the sender binding definition, you have to take some assumptions for Facebook, right? Because if Facebook does not store the ciphertext correctly, always the sender can sync with the receiver, right? Assume that Facebook is doing everything properly.
Yeah, so you don't have to trust. What do you mean by trust Facebook? Because sender binding is really about an adversarial recipient.
But that
So
goes through Facebook. So all the messages have been received by the receiver through Facebook. So
yes,
you have to assume that Facebook and the sender do not go into Facebook.
that the Facebook and the sender did not collude. Yes, if Facebook colludes with either party during abuse reporting, all bets are off, right? So we're trusting them during abuse reporting, but not during non-abuse reporting. That's when we want to have security guarantees from Facebook. Yeah, good question. Okay, so how do we do this? The first thing is obviously, ASGCM is used like all over the planet now, right, for TLS and other things. So it may seem weird that we're saying we're going to exploit ASGCM to do attacks. Isn't this actually secure? And yes, it is secure by our standard notions of security, but this is a very special property that we're asking for. In particular, the usual security guarantees for authentic encryption hold when you have a secret key that is not known to the adversary. But in Facebook's message franking protocol, the sender gets to choose the secret keys. So we're in this special place where I can choose the secret keys, and I'm asking for additional security properties from this symmetric key primitive, even though I know the keys. Technically, what this is called is robustness in the cryptographic theory literature. It's been studied previously by a sequence of papers. And the idea is, if you have a robust authenticating encryption scheme, that means it's one for which no efficient adversary can find a ciphertext that decrypts, to anything but an error under two different keys. So it's actually pretty precisely the property that was missing from as we'll show, from ASGCM, and that enables this attack and is related to this compactly committing authentic encryption that we'll deal with next. Okay, so let's start with a warm-up, which is looking at robustness for counter mode encryption, one of the most basic encryption schemes, not an authenticated encryption scheme, just a regular encryption scheme. If we have a block cipher like AS, it takes n-bit inputs and a secret key and outputs n-bit outputs. How do you use it to encrypt something? You have a counter, you encrypt like 1 under using the block cipher, you get like an n-bit output, you XOR that with your plain text, you get a ciphertext block, and etc. Okay? Very standard thing. So how do we do a robustness attack against this? Well, it's actually totally trivial to do a robustness attack against these unauthenticated encryption schemes. Just pick an arbitrary key, K-file, pick 2 blocks of plain text, encrypt those to get a ciphertext, C1, C2. Pick some other key, K-file 2, and then output that now tuple, K-file 2, C1, C2. And because there's no authenticity checks or anything, like you decrypt C1, C2 under K-file 2, and you're also going to get back a legitimate plain text, right? The ciphertext space is dense. Every ciphertext is a valid, every string actually of 2n bits in this case is a valid ciphertext for any key. Of course, you get a chosen plain text and a random plain text, which may not be good for the semantics of your application. We'll come back to that issue later. Okay, so that's counter mode. They're not using counter mode, they're using ASGCM. which is a more complicated authenticated encryption mode, but it does use counter mode as its first layer of like encryption. And then what it uses is this thing called GMAC or Galois MAC, which is a universal hash-based message authentication. So this is there to try to prevent people from manipulating ciphertext bit values. Just some notation, this H value is basically the application of AES on the string 0 to the 128. And this gives us a point, and these multiplies are actually field multiplies in GF 2 to the n, or 2 to the 128 more precisely here, which is basically how they do the processing of the ciphertext to get kind of a short, compact n-bit digest summary of it, which they then protect with this pad, which is the E sub k of a counter value. Okay, and then that final output is this authentication tag, which is also part of the ciphertext, right? So to do our attack, we need to not only generate counter mode ciphertext blocks like ciphertext 1, ciphertext 2, but also a tag that is correct under these two different keys, okay? So if you haven't seen universal hash functions before, that's fine. The point is we can actually just rewrite this as an equation of the variables. So the tag is equal to this polynomial equation relative to this value h, this key h, and pad, and the ciphertext blocks and this length field. So because it's a universal hash and it has this nice algebraic structure, we're able to do some nice things in order to derive an attack. So what do? As before, we just basically pick an arbitrary key, k file, and then we derive the associated GMAC keys h1, pad1. We can pick one block of plain text, the first plain text block, say. And let's let C1 be the ciphertext block associated k file. Also C2 should also be the ciphertext block associated with k file. And then we can pick a key k file 2 and then derive the associated keys for this. And then we're going to solve the tag equation for C2, okay? So what does that mean? So we're going to think that we have one ciphertext here, C1, C2, tag, right? 3 values. And we have 2 different keys, H1 and pad in 1 in red, and H2 and pad 2 in orange, okay? So we want to have the same tag value, okay? But this ends up being a linear equation in one unknown, which is C2 in this case, because I chose C1. So the only open variable here is C2. Everything else has been defined, but it's a linear equation. I can just solve for C2 and I get some value and this is fine, okay? This is all a very long way of saying that these universal hash-based functions are not collision resistant if you're a cryptographer. And it's easy to find collisions if you know the keys, okay? It's not a property it's designed to meet. It only provides good security properties when H and pad are unknown to the adversary. Okay, so in the end I can do all this. I can output K file, K blah blah, the stuff written there, and these will, the ciphertext C1, C2 tag will decrypt properly without error under K file and K file 2, okay? And so we violated robustness of ASGCM. Okay, so to reiterate back to the high level, what does this give us? This gives us the ability to generate, ciphertext that we can, and 2 keys, such that we can send this ciphertext twice in 2 different attachments. The victim will see both associated plaintexts because they decrypt properly. But when the abuse report comes, because there is only one ASGCM ciphertext string, only one of the 2 plaintexts will be included in the abuse report. And so we've succeeded in violating sender binding. So in this attack, the second bit string, the second plain text is just a random bit string, and that seems a little unsatisfying. Actually, it was sufficient to convince Facebook to change things, but we wanted to have a cooler looking demo, so I forced Paul, the student, to work harder to get it working, to have a chosen second message, something that's like semantically meaningful, a valid image. And it turns out you can do this. It requires a bunch of trickery with the image file formats and kind of putting random noise in places that don't matter when you parse the image and these types of things. I'm not going to go into the details. You can look at the paper if you're interested in that type of hacking. But what the eventual thing is able to do is you can send both of these. You can basically construct an ASGCM ciphertext that decrypted under one key gives you this horrendous looking salamander, axolotl, poor guy, And the other, under the other key, the same ciphertext decrypts this kitten. Yeah, same thing. So just as a backdrop of why we kept talking about invisible salamanders, axolotl is this endangered salamander species. This is the name of the Diffie-Hellman ratcheting thing used in Signal. I don't know why. You have to ask the developers, Trevor and Moxie, thank you. And then the Facebook Messenger code, they actually refer to secret encrypted messages as salamanders. So hence the title, like invisible salamanders. Yeah. So again, takeaway, you can send this guy and can't get reported. So we did a responsible disclosure. And in fact, we were talking to John Milliken, particularly, who works on the team a lot, and we thank him for answering a lot of questions about how this works. They actually gave Paul a bug bounty. Faculty don't get money anymore, I guess. I think he donated anyway to the libsignal.org or something. But anyway, got a bug bounty. So they took this as a serious vulnerability. And from my perspective as a cryptographer, at least for the purpose of this talk, it seemed to me that this was they were basically implicitly making assumptions about the cryptographic properties of ASGCM that led to this vulnerability. And so one way to try and approach this and have more principled thing is like, hey, let's step back, think about what it is they're trying to build with this message franking type authenticated encryption, and try to cook in the required properties right away so that you have everything that you need. And so that's what I'll talk about in the remainder of the talk is doing that. So again, the basic thing is we're combining authenticated encryption commitment. So they didn't actually use this for their attachments. If they had, there wouldn't have been a problem actually. And the reason they didn't do it is because it's too slow, right? They do an HMAC, they do an AES CBC, which is another encryption mode like counter mode with similar performance profile, and then another HMAC. And in symmetric crypto land, this is very heavy. This is expensive, and John said this is considered too slow for large image and file attachments, so they didn't want to do it. Or maybe it drains too much battery or something. But anyway, the performance profile is insufficient. So we'd like to do better from a performance perspective. So that's one of the other goals here is, if we can provide a good framework for designing what type of properties we need, maybe we can do better than this kind of thing of combining generically authenticated encryption and commitment. And so towards that, we introduced this new primitive that we call compactly committing authenticated encryption, which is a bit of a mouthful. So I'll say CCAE, which is also kind of a mouthful. So I'll just go over briefly like the basic syntax and semantics of this new thing, like what are the algorithms and how are they supposed to work. I'll talk about the security properties, and then I'll talk about whether existing schemes like kind of satisfy already the properties that we want. Maybe ASGCM doesn't seem to work very well for us as in this context, but maybe other ones do. And then I'll show just our latest, fastest, what we think is currently the most elegant approach for this, which we believe satisfies the performance requirements of Facebook and others. Okay, any questions before I move on? Yeah?
How about ASCCM?
That would also be vulnerable, yeah. So basically any scheme that's using like a non-collision resistant, as we'll see in a moment, there's a connection. The non-collision resistant message authentication code is very likely to be vulnerable. We didn't work out an attack, but I'm pretty sure I could if I sat down and did it. So it's not just universal hash-based message authentication code. The CBC is also kind of not, it's easy to find collisions if you know the key for ASCBC MAC. Yeah, great question.
So you could use maybe something like sponge functions? Would that be possible?
You can, and we'll actually get back to that. Yeah, so Sponge is there's a variant of the Sponge, this so-called duplex mode, which was kind of this one-off paper, or paper that hasn't gotten as much attention, maybe it should, that actually satisfies the properties we need. And we didn't realize that until after we designed ours too, which is, they're very related, but I'll mention it briefly later, yeah. Good. Okay, so if we return back to just reminder about what is authenticated encryption, formally it's a triple of 3 algorithms, right? Key generation, which for our purpose is always just choosing a random bit string, essentially of a certain length. Then you encrypt under a message under the key, get a ciphertext, and then you can decrypt that. Typically, encryption is randomized, but it can also be non-space and these other things. And decryption, I should say I didn't show this, but decryption can always throw an error too. It can output like some error, like this is invalid ciphertext. Okay. We're going to change this a little bit for compactly committing authenticated encryption. key generation is the same. Encryption now outputs not just a ciphertext, but also a distinguished thing that we're going to call a binding tag, okay? And this should be short. That's the whole idea why we keep saying compact, right? It should be like 256 bits. And the reason for that is it's a performance thing, right? Because I remember way back in the beginning I said that Facebook needs to sign this C sub B value. So if C sub B is like as long as the message, that's asking them to do a lot of work, but we can get away with a very fast signing operation if we can have the binding tag short, which we will be able to achieve. Decryption now takes this pair, CCB, the full like ciphertext and binding tag, and outputs a message, but also an opening key, okay? That's for verifying the binding tag during abuse reporting. And then there's this verify algorithm, which is going to be run like by the service provider, right, where it gets the message and the binding key and the C sub B and outputs, yes, it's a good opening or not, okay? Right, and so, more generically, you can just imagine we're going to replace, this authenticating encryption plus C sub B with some generic CCAE scheme at the front, but otherwise, and purposefully, it doesn't change much, that picture, right? How you use it in the message franking protocol flows. Okay, so good. One last thing is that, as I mentioned, encryption in general can be deterministic or randomized. For the purpose of the talk, I'm just going to kind of gloss over this and consider deterministic encryption, which in general is not sufficient, but actually in the case of in Signal, it actually is because you only ever use a key once with every message because of ratcheting. You only ever use a key once because of ratcheting, but anyway, it just kind of simplifies the notation. But in the papers, of course, we go into much more excruciating detail on using randomization and everything. Okay, so what do we want from this in terms of semantics, right? Like obviously we want some type of correctness guarantee so that it should return the correct message when you do decryption. And that also here, additionally, that it should, openings should verify if they're honestly generated. And again, we have this compactness guarantee that I keep harping on. And then things start deviating a little bit in the sense that there's multiple viewpoints you can now take on what this binding key, this opening K sub B thing is going to be. In the case of Facebook scheme, we had what we'll refer to as kind of actually a multi-opening CCAE scheme, which means that the secret key that's used to do encryption for confidentiality and authenticity is actually different from the opening key. Right? Remember, they chose a separate K sub B. And it's actually kind of interesting because you can achieve, even though they didn't need it in their application because they only used K once ever, you can basically do an opening relative to some scheme that uses key K, and then keep using K for more encryptions and still have confidentiality and authenticity guarantees, which I think could be useful in some applications. Another approach is that you actually just merge these two, right, which is probably the more natural thing to think of, at least from for me, that the binding key actually just ends up being the encryption key. But of course, this obviates all security of the underlying for future messages. So you'd only ever want to do this if you were truly only ever using the key for one message and that message is getting reported. So again, for simplicity, we'll just focus on this case in the talk, but the papers go through the other case as well. Okay, so in terms of security, we want for single opening, it actually kind of matches the traditional notions of security for authenticating encryption, following this work by Rogoway and Shrimpton from 2006, which basically says, that the ciphertext to someone who doesn't have the secret key should be indistinguishable from random bit strings. Okay, and this is a very strong security guarantee, confidentiality guarantee, and moreover, that no one who doesn't have a key should be able to generate a valid ciphertext. Right? The only way to get a ciphertext that's valid is to have actually generated by someone who has the key. So these are pretty standard. The new thing is these kind of binding notions that correspond to the new kind of opening and abuse reporting properties that we want. And there's two properties. The first I'll refer to is the sender binding, which is a bit simpler, at least at this level. And this is kind of can be formalized by a security game that looks something like this. Adversary A basically gets to choose a key, okay? So this is really deviating from the standard security models because the adversary gets to pick the secret key and a ciphertext. And then that ciphertext will get decrypted by running the decryption algorithm. This could throw an error, right? Because it could be an invalid key ciphertext paired, right? In which case the adversary loses the game. Otherwise, the game will then run this verify procedure and if verify comes out to be false, then the adversary wins the game. And otherwise the adversary loses. So what is this modeling? This is modeling the idea that we don't want adversaries to be able to come up with ciphertexts as a sender that decrypt to something besides error, but are not reportable. Like the verification fails, and like they would get rejected by Facebook when you reject. So intuitively, this is what, if you think about the high-level sender binding property that we talked about that was violated, this is that property projected down onto the primitive of compactly committing authenticating encryption. Now the good news is that this is very easy to achieve as a property. Why? Well, because you can just always check the tag when you're doing decryption. If you check the tag during decryption, then there's no way for verification, if decryption succeeds, for verification to not succeed. So you just always check the binding tag, right? It's kind of simple, but it's very important. Actually, we had some schemes early on that we were designing that we didn't achieve this property. We realized like the night before the deadline that was no good. So it's an important property even if it's easy to meet. And of course you want to do that efficiently. So ideally, like during the decryption, normal decryption process, you kind of end up implicitly verifying the tag, and we'll get that. Okay, and then there's this receiver binding property, or strong receiver binding, which again we can formalize with a game. Then an adversary A gets to output a pair MK and a pair M prime K prime and a binding tag, just the short binding tag C sub B. And basically wins if the MK pairs are distinct. Okay, MK is different than M prime K prime. And they both verify for this single C sub B value. Okay. So this is again, this receiver binding, so the recipient shouldn't be able to like come up with two different ways to open a single ciphertext, okay? And this is important. There's this technical thing, this is what we call strong receiver binding. If you kind of get rid of the keys from this requirement, you get what we call regular receiver binding, but I'm just gonna forget about that actually. Okay, so this is important. If you're looking at this, and you may think of collision resistance a little bit, because this actually looks a lot like a collision resistance property. And in fact, there's this very clear connection with collision resistance. When we found the attack against ASGCM, why? It was because the universal hash-based MACs are not collision resistant, and that's allowed us to generate these colliding ciphertexts, right? Two different keys, two different messages, same ciphertext. There's collisions happening. So formally, if we think of verify for our CCAE scheme as being something that basically implements some deterministic function over the message and the key, and then checks does that equal the binding tag, then, and if so, then return 1, it's verified, and otherwise return 0. For these types of CCAE schemes, then you get this dual implication that the scheme is SR bind if and only if F is collision resistant, this function F, whatever it may be. I haven't specified what it is. I'm just saying you can rewrite verify in this form. And CR, again, is just that no computationally efficient adversary can find two MK pairs such that F that are distinct such that they collide under this function. Okay. And if you can think back to Facebook's scheme, right, they used HMAC for this, so you can just set F to HMAC, and that's essentially what they did. HMAC is a good CR function if it's built from a good hash function like SHA-256, and so actually you get kind of SR bind security very easily. It's very easy to show for their basic scheme. But remember, they didn't use their basic scheme for file attachment, so got really close, but not all the way. Okay, there's another benefit of this viewpoint, which is that, before that, we can kind of go back and think about regular authenticating encryption schemes, the CCAE schemes. We can decide whether they are, and how do we do that? Well, we just think of the authentication tag now as a binding tag as well, right? So for ASGCM, we can think auth tag, maybe it was good enough to be also a binding tag. We saw that wasn't the case for ASGCM, but it may be true for other schemes. And so we went back and looked and kind of reconceptualized existing authenticating encryption schemes as CCAE schemes, and figured out whether, most importantly, they're receiver binding or not, because that's kind of the key property that's hard to achieve here. So ASGCM we saw is not. OCB, which is another very fast scheme, is not. Typical things like encrypt and HMAC, when you use two different keys, one for encryption and one for HMAC, is also not receiver binding. Interestingly, if you use the same key and then derive two subkeys using a hash function, so-called one key, it actually is receiver binding. And finally, the Facebook scheme, which I already alluded to, is receiver binding. I emphasize this fourth one because actually that is the scheme that's used underneath Signal. And so in some sense, actually, they could have just used the existing crypto that was being used to process messages for binding. There may be some optics issues with using the key for encryption and as the revelation in the opening, but we thought this was interesting. Nevertheless, this is still not as fast as we might hope for, right? We see some authentication encryption schemes that have one pass, right? They just take one cryptographic pass, sort of like a block cipher-based application for each block of input plaintext. And encrypt HMAC requires two. We show that via this connection to hashing that actually you can exploit previous impossibility results to rule out not just that AES, GCM, and OCB don't work, but any schemes that are similar. As these. They just use a block cipher with like a single key to process every block of message. All of those things are not going to be sufficient because of this connection with collision-resistant hashing. And this harkens back to these impossibility results that were very nice about block cipher-based hashing from the mid-2000s. Yes?
When you send a file with Signal, do they use the same encryption scheme?
I can't hear you, sorry.
When you send a file with Signal, do they use the same encryption scheme, or do they, like Facebook, use a different scheme?
No, they use the Signal library. They use libsignal for the actual underlying encryption.
Oh, I see.
Yeah, and libsignal uses encrypt then MAC. Yeah, exactly. Yeah.
So there is this notion of these non-misuse resistance AED schemes, especially these synthetic IV
Right.
things,
Yep.
also from Roboway and
Yep. Yep.
And that looks very similar to what you do here.
Yep.
Because you would first generate the synthetic IV, which is basically a macro with a message,
Yeah.
and then use that IV
Yeah.
to
Yeah.
feed it as a nonce into the encryption function.
Yep.
Which seems to be
So that will work if the generation of that synthetic IV is a CR, is collision resistant. So like SIV mode would not be because they use this like PMAC kind of thing like CBC MAC. Yeah. Okay, so anyway, it was kind of disappointing to us that we could rule out the fastest authenticating encryption schemes, but we're going to try and get as close as possible. And that is our where we get to with our kind of proposed fastest scheme at this point. We've actually suggested a few schemes over the course of these two papers, but this is the one I'm most excited about. And in the end, because what we can do is just use a single hash computation over the message, basically. Just think of one SHA-256 over the message, and that's all you need to do everything: encrypt, commit, yada yada. So let me show you in the I got time. Good. So let me show you what we do, and we call this the hash function chaining. And if you've seen this duplex mode, it's similar but not exactly the same because we start with different primitive. So let's recall how hash functions are constructed. Okay. At least the Merkle-Damgard style ones like SHA-256 and SHA-512, which are used all over the place now, and also SHA-1, but you shouldn't use SHA-1, right? Because it's not CR anymore. And what do we do? There's a two-step process. You first specify a compression function, which is, it is itself a hash function, but works on a fixed input length of, like, say, n plus d bits. And then you iterate this fixed input length compression function multiple times in this type of Merkle-Damgard style mode in order to hash a longer message. Okay? So this IV, which is what's the first chaining variable, what's called a chaining variable, these values, here. IV is just a fixed constant value, and this is how you compute the hash on a larger message. Okay, so we're going to convert this into a CCAE scheme, okay, in the following way. Oh, I should say before that what do we know about these things? Well, if F is kind of strong enough, then the whole thing is CR. This is a classical result back to the 80s, okay? And so this is what supports, from a theory perspective, at least, like why SHA-256 and SHA-512 are good. We put some emphasis on F being secure, and as long as F is secure enough, you get the iteration being secure. Good. So how are we going to convert this? We do kind of a three-step thing. It's actually pretty straightforward. We first prepend the message with a block of zeros, and then we XOR the key into now this prepended message, block by block. So what that means is that eventually you're going to hash like the key, and then key XORed M1, and then key XORed M2, and then key XORed M3. We're going to then use the chaining variables now as pads to encrypt the message blocks, the next message block. So this output value here we're going to use as like as a pad now to XOR with the next message block to get our first ciphertext output. Okay. and then move on and so on, okay? Which is a very strange thing to do. I mean, this is not what you use hash functions for, but was kind of the key insight and how to get it as efficient as possible here. And then finally, the output is just our binding tag, C sub B. Yeah, after we looked at this, we realized it's a lot like the duplex construction, though the details are different. They had similar intuition, really nice. Though they didn't have this application, so we need some adjustments. Okay, so yeah, encryption just requires a single pass of the hash function. Obviously, I'm showing you deterministic encryption here. There's no randomness, per message randomness, but it's easy to add. You can see the details in the paper. So what's the decryption and verification are also very simple. Decryption, right? Well, if you get these guys, right, and you know the key, well, you just compute forward. Now you know this, XOR with this to get that, and you can compute forward and go on, right? So decryption works. And just make sure at the end that whatever you compute at the end also matches the binding tag that was in the ciphertext handed to you. So importantly, for sender binding, we're checking the tag, right? But that's providing both authenticity here as well as binding. And then verification, you just recompute the hash over this key XOR thing, and you're good to go. Very simple. Okay, so how much time do we have? A few minutes. So let me just go over very high level intuition about security, right? There's 4 security properties, right? Confidentiality, integrity / authenticity, receiver binding, sender binding. Confidentiality we get because if you make a suitable assumption about the underlying compression function, for people who are cryptographers in the room, what we assume is that it's a related key attack secure pseudorandom function for XOR related key functions. For everyone else in the room, you can just think of if f, when we do this weird thing with the k XOR m's, acts like a random function when you don't know key k, then these chaining variable values are basically random values that the adversary doesn't know what they are, so it works as a one-time pad, up to at least having some collisions in chaining variables, which if these chaining variable things are long enough, doesn't happen, okay? And so that's nice, we get confidentiality. Integrity, intuitively, you're basically building a MAC out of this a message authentication code directly out of the hash function, and so this C sub B actually serves as an authentication code as well as a binding code. And also, there's this kind of interesting theoretical thing that is in the paper, which I won't mention further. So that's good. Receiver binding. Remember, we have this collision resistance property. The only thing we have to be careful about here is the fact that we're doing this encoding of the messages. If it was just the message being stuck in here with the key, then it would be okay. But that's actually not much of a problem because this encoding, by prepending the key k here, it ensures that this encoding of k comma m is injective, okay? Which means that it's one-to-one, right? There's no way to, if you didn't have this k here, and you just started with XORs, there would be trivial ways to find collisions and break receiver binding. That would be no good. But that's the reason we do the prepending. And then that combined with obviously the collision resistance of the underlying hash function gives us what we need. Good, very simple actually. And then, yeah, as I said before, we check the binding tag during decryption, so we get sender binding. Yay. So actually, the proofs are relatively straightforward, which I consider a huge advantage, particularly for things that we want to deploy so people can understand what's going on. And importantly, that I can understand what's going on. So anyway, summary of scheme. So we have this thing HFC. If you use SHA-256, this is really simple and fast. As I mentioned a couple times now, there's this, we realized actually in the course of this work, after we'd done a lot of this, that this SHA-3 duplex mode in this paper from 2011 does something very similar, and so we can actually analyze it from the lens of CCAE, and it provides the right types of properties. So if you want to use the SHA-3, there's a way to do it with duplex. If you want to use SHA-256, SHA-512, we give a way to do it. And these things we believe are, certainly fast enough to use for anything reasonable, and would definitely, they're not quite as fast still as like OCB and ASGCM, but they're very fast, and they would certainly prevented this attack actually. So that's good. Okay, I'm glossing over like lots of details. Obviously state-of-the-art authenticating encryption, there's lots of different variants of authenticating encryption now. Like one notably is that most authentication encryption is actually authenticating encryption with associated data. We have this like inflation in the number of adjectives we stick around authenticating encryption. In the paper we handle that, we do CCAE AD. We haven't looked at all the like misuse resistant stuff, but I think that should fall out pretty easily, or variants should fall out. There's other schemes that we looked at that are fine. You can look in the paper in details. The multi-opening security actually requires new confidentiality and integrity notions, so we can't just rely on old notions. So there's something new to do definitionally there, and it actually makes proofs a little bit more complicated and nuanced. But I'll refer to the papers for that. And then finally, from a theoretical perspective, we actually took another step to kind of formalize an even simpler primitive than CCAE that we call encryption. That was Yevgeny's idea to call it encryption. He thought it was very clever. It grew on me over time. So if you don't like it right now, give it a few days. From a theoretical perspective, it's very interesting because it's kind of the simplest primitive that gives you what you need. It's like kind of a one-time secure CCAE. It simplifies all the definitions, makes our proofs kind of very modular and easy to follow. And has applications to other settings, which is nice. Okay, so summary, message franking is this neat thing that Facebook kind of started that allows verifiable abuse reporting, which helps resolve, this tension between end-to-end confidentiality guarantees and the need to help out people who are, getting abusive messages if you have like a service like Facebook that wants to be able to kick people off the network for being jerks. It's it's a little subtle to get right. They got almost all the way there, but then missed this case due to what we think is kind of a implicit, like they made this implicit assumption about properties of authentic encryption that weren't provided. We think you can do better, but our approach of like kind of formalizing stuff and working up from there. And anyway, we have a new scheme that we think will hopefully be useful and deployable. So right now we're working on implementing kind of not only HFC, obviously that should be very simple, but also the surrounding kind of libraries and stuff you need to provide kind of an open source version of what Facebook did. So there'll be at least a reference implementation of kind of how to do abuse reporting. There's lots of things to work out there, and we're working on it now. So thank you very much.